This is Bryce Bailey with my second physics video lab report. Today in Tracker we're going to be modeling the motion of a tennis ball as it falls and paper as it falls, with paper having a much faster trend towards terminal velocity due to heavier air resistance. If we observe the video here, let me back that up. We can see the ball falling at a steady rate. We have calibration stick here set to 0.9 meters, which is about the width of this door. Now if we watch the falling motion of the paper, it obviously moves a lot slower, drifts around a little bit, hits terminal velocity rather quickly. We have both of them modeled on the negative y-axis, and we're just going to ignore any change in the x values due to the drifting of the paper or the unevenness of the camera when talking about the tennis. Here we have the data and the graphs that we have modeled from the two videos. This is the model of the tennis ball. As you can see, it starts to go more towards a 1-to-1 ratio in the line, which shows a slow approach towards terminal velocity, while as the paper, illustrated by this graph, moves there rather quickly and kind of straightens out a lot faster. If we go to our Python program, where I have accounted for viscous drag here by making the constant of proportionality equal to the velocity, making the net force equal to the gravity plus the drag right there, and then making the velocity a change due to the net force. If we run this, we can see a slow buildup of drag until it evens out with the force of gravity and hits a nice terminal velocity right there. We've modeled the data points from this further down, and we can also see a curve into a nice straight line like that, which is more closely represented by the tennis ball model from our earlier videos than the paper is, due to the paper having a lot more air resistance and not having that regular approach towards terminal velocity. Now, if we were to remove the force of drag, which I've done here by setting it just equal to 0, and also getting rid in some other places in the code of the arrow representing the drag, we can model it then and see a very different action where the force of gravity is constant and we continually speed up. We can then go into an Excel sheet where we can model the motion of that. Second. Represented as a scatter plot. And you can see it continually goes faster because of the gravity force acting on it, whereas with the drag we have a nice even out into a terminal velocity. So the difference is quite clear as to the effects of drag on tennis balls, for example, which without it would increasingly speed up as they go closer and closer to the earth. So what does all this mean? Well, essentially it means terminal velocity can be altered when an object is subjected to air resistance. Because if we just look at these two graphs, we can see that the tennis ball takes a certain time interval before its velocity is constant, whereas for the piece of paper, it approaches that terminal velocity much more rapidly. So when approximating an object's future position and speed, you have to take into an account how air resistance is going to affect it, because terminal velocity can put itself on an object at very different rates depending on how the air resistance is subjected to. Now, what if we threw the object in question instead of dropping it? How exactly would the model change? Well, if we go to VPython, we can see that I've changed the vector to -10 for its initial velocity, meaning it's going to have a very different effect the air resistance is going to have a very different effect on the ball. Now, if we run that, we see that the drag starts off at a lot higher rate than the gravity. It still approaches terminal velocity, but does so much faster due to the fact that the drag is at the initial point actually greater than the force of gravity, and we have this curve that is a little more in this direction than we would normally see. Removing the drag from this thrown object gives us a model that's a little less interesting, as the gravity has the same effect. It's just the ball starts off moving a little bit faster. It still never hits terminal velocity due to the fact that there's not a drag, and is not really much different of a model than the one we looked at earlier of gravity acting on a ball without any initial thrown. So thanks for watching my video. I hope you guys have learned something, enjoyed it, and I'll see you guys next time.